In today's lab, we will study motion on an incline. Our main goals in this lab are to understand the relationship between position, velocity, and acceleration, interpret plots of these variables, and measure the acceleration of a cart down an incline as a function of angle. To learn about position, velocity, and acceleration, we will take the motion of a car as an example. It starts from rest, accelerates to a constant speed, moves at that speed for 5 seconds, and then comes to a stop before the stop sign. First, we will consider how the position of the car changes over time. During acceleration, the position has a quadratic form. At constant velocity, or zero acceleration, the position is linear. Next, we look at how the velocity changes over the car's motion. During the acceleration, the velocity increases at a constant rate of 3 meters per second each second. When the acceleration is zero, the velocity is constant. Next, we consider how the acceleration changes over time. It starts at a constant positive 3 meters per second squared, goes to zero as the car moves at a constant velocity, and then goes to negative 3 meters per second squared as the car stops. Let's bring all these plots together to look at the relationships between position, velocity, and acceleration. The instantaneous velocity at some time is the slope of the position graph at that time, while the instantaneous acceleration is the slope of the velocity. If we calculate the slope of the velocity curve during the initial acceleration, we can see that the velocity increases 3 meters per second each second. This gives us an acceleration of 3 meters per second squared. We can now watch the graphs evolve as the car moves, noting the differences between regions of constant acceleration and zero acceleration. Now we are ready to explore the equipment you will use in this lab. The cart and the track ends each have magnets which repel each other. Attach the metal reflecting vane to the end of the cart. This provides a surface for the motion sensor to measure. Be sure to catch the cart before it hits the end of the track. When released down the incline, it will have enough momentum to overcome the force of repulsion from the magnet. You will use the clamp and metal rod to elevate one end of the track. Open the jaws of the clamp and then attach the clamp to the table. Insert the metal rod in the hole in the clamp and tighten. Check that both the metal rod and the clamp are secure. There is a hole in the clamp attached to one end of the track. Slip this hole over the metal rod, move the track to the desired position, and tighten. Your TA will give you 3 angles at which to measure the acceleration. This angle is measured between the table and the track. Use trig to determine the height needed for a given angle, and use a meter stick to verify you have set the track at this angle. Once you have the track set up, you can connect the motion sensor to the Pasco interface. Loosen the screw on the left side of the motion sensor to adjust the height. You can also adjust the tilt of the motion sensor. The sensor should be tilted at an angle parallel to the track so that you measure the distance the cart moves along the track. You are now ready to take data. Let's release the cart from the top of the incline. Attach the reflecting vane to the cart and make sure someone is ready to catch the cart at the bottom. Let's watch that again at half the speed and take a look at what we will see in Data Studio. The top graph in the Data Studio window is the position, the middle graph is the velocity, and the bottom graph is the acceleration. Let's take a closer look at these graphs. As we saw with the car, when moving under a constant acceleration, the position graph has a quadratic form while the velocity graph is linear. To find the acceleration, we just perform a linear fit of the velocity for the time the cart was rolling down the incline. The acceleration for this period is just the slope of the velocity. Once you measure the acceleration at 3 different angles, make a plot of the acceleration as a function of angle. What do you notice about your data? We will discuss the physical basis for your observations later in the semester when we cover forces.